Okay, I did want to run out of time, so I started a new video. So let's go through the worked example. So we're going to find the long-term Leslie matrix trend. So we've got an initial state here, and we want to show whether in the long term, the population will increase, decrease, or cycle. So we've got three different Leslie matrices here. So L is a 3 by 3. So S3 using the Leslie matrix rule. So S of n equals Leslie matrix raised to the power of n, so how many cycles we're going to go through, multiplied by our initial state. So we're going to go S of 3, so Leslie to the power of 3 multiplied by our initial state. So if we have a look at this, we've got them back to, so S of 3 and S of 0. So S of 0 and S of 3 are the same. We actually end up with the same. So the population is going to cycle every 3 time periods. Okay, so if we go back to this rule, if S of M, so the size of our matrix, so because we're working with a 3 by 3 matrix, we went to the third, we raised it to the power of 3, so we went through 3 iterations. Because they are the same, it is going to cycle for that number of time periods. In this case, it's a 3 by 3 matrix, so it's every 3 time periods. So now, again, it's a 3 by 3 matrix, so we're still working to the power of 3. We're going on to our second Leslie matrix. So we end up with, once we create that calculation, can you see that we've got this matrix? So the total population at S of 3 is 600, and the total population at our initial state was 1200. So 600 is less than 1200, so our population will decrease. So this one here, so if S of M, so M being the size, we're pulling that from the number of rows or the number of columns, is less than the total population, it's going to decrease. All right, and then the same thing here, we've got a 3 by 3 matrix, so we're going to raise it to the power of 3. When we get our solution, can you see that it's now larger? So because this value is larger than this value, in the long term, our population is going to increase. So long-term Leslie matrix growth rates. So we've seen for regular transition matrices in the long term, the state matrix gets to a point where it stops changing from one transition to the next. With Leslie matrices in the long term, the numbers in the state matrix generally keep changing, but the proportion of the population in each group will actually stabilize so that we can calculate long-term growth. So can you see here, we've got state matrices for two large consecutive values. So we've got 29 and 30. So we can calculate the growth rates for each of the age groups. So we're taking this value here divided by this value here, gives us approximately 1.1501. We do the same with the next age group and the final one. So can you see how we've actually stabilized with the proportion of people in there? Okay, so when we talk about these, we're talking about the growth rates for each age group. So these values are the same to the 3 decimal places. So we've found the population has a long-term growth rate of 1.15, which means that after a certain time, the population is always going to increase by 15% each time period. So long-term growth rates less than 1 are a percentage decrease. So see how it's 1.15, which means that there's actually a 15% increase. If it didn't have that 1 at the start, so it's less than 1, it will be a decrease. So you can see here that 0.92 minus 1 times by that 100% gives us negative 8%, which means that the population is decreasing by 8%. So long-term Leslie matrix growth rates. So for two state matrices with large consecutive values of n, so say we've got 49 and 50, so raising it to the power of 49 and 50, we've got each of the elements in Sn plus 1 over the matching element in Sn equals the same value of G, then G is the long-term growth rate of the population each period. So up here, so we've got this value over this value, this value over this value, this value over this value. So we're talking about Sn plus 1, so that was the next number over the previous number. If it's the same value, then G is the long-term growth rate of the population. So each of these, G, is the same. So we've got the long-term growth rate of the population for each time period. To calculate that percentage increase or decrease, we take that G value, so whatever we got, which was the same, subtract 1, multiply it by 100 to get either the percentage increase or percentage decrease. So if G was greater than 1, the population is increasing. If G is less than 1, the population is decreasing. If G was equal to 1, the population remains stable. So here we go. Worked example 17. We've got an initial state matrix and a Leslie matrix, and we want to find the long-term growth rate per period to 2 decimal places. So we've got our initial state, our Leslie matrix, and we're going to find the percentage increase or decrease per time period to the nearest percentage. So our 2 consecutive values, we've chosen 29 and 30 in this case. Remember, you can choose any values. They just have to be large enough and they have to be consecutive. Consecutive being 29, 30, 49, 50, 112 and 113, for example, just have to be consecutive. So we've got our S of 29. So we're raising our Leslie matrix to the power of 29 multiplied by our initial state. We get this matrix here. We do our 30 matrix here. So remember, we have to take each element from the same, whether it be age group, whatever they're talking about. So we've got 154, so 154,916 over the 132,103. So this one being that it is the 30th iteration over our 29th iteration. So this over this, this over this, this over this, and we get each of those. Can you see that they are very, very similar? So to the 3 decimal places, actually 4 decimal places, they are the same, which means that we have a long-term growth rate per time period, which is 1.73. The question asked us to go to 2 decimal places, so we round to the 1.73 because the 6 tells us to take the 2 up. So our long-term growth rate is 1.73. Then we're going to calculate that as a percentage increase or decrease. So we take G, being this value here, which is the 1.73. So 1.73 minus 1 times 100 gives us 73%. So because this value here was greater than 1, we know we've got a percentage increase, and it's a 73% increase. So per time period, our percentage is increasing by 73%. All right, that was Leslie Matrices. For the SAC, Leslie's aren't coming into it. You will see them in the exam though, so don't forget them. But go back to the screenshot that I shared with you on what you really need to hone in on for your SAC. I've uploaded the suggested SAC solutions, so start having a go at what you've done and see how you're tracking. Remember, all of the SACs for this subject are going to be that more investigation style. Don't be disheartened with your results if you are finding the investigation style difficult. The exam still comes back to one that is multiple choice and one that is more of a short answer. And they are moderated against, like your SAC is moderated against your exam results. So you have the opportunity to demonstrate your knowledge in those exams. So please don't be disheartened because you are finding investigation style difficult. Your SAC result doesn't necessarily translate to a poor study score if that makes any sense to you. But don't be disheartened with SACs automatically precluding you from chasing a strong study score. But you will need to put the time into revision and studying for those exams and getting the best exam score that you can. We can do a little WebEx if you want me to explain it a little bit more to you. But now is the time to perhaps come back to Leslie Matrices questions later on. I want you to dig into that revision so that we can get our SAC underway very, very soon.